Hello, class. I'm just going to pick up where we left off in the note packet. So here, we have an example. A sled with mass 22 kilograms is pulled across level ground by a child who is applying a force of 110 newtons at 55 degrees above the horizontal. Coefficient of kinetic friction between the sled and the ground is 0.3. What is the magnitude of the sled's acceleration? Now, this is pretty similar to this problem right here, but now the force is at an angle above the horizontal, so it will be slightly different. But let's go ahead and draw our free body diagram. Note that the force is angled, the ground is not. That's something that students tend to make mistakes on. They see the 55 degrees and they immediately draw an inclined plane, but that's not always the case. Anyway, so the forces acting on the sled are gravitational, normal, of course. This applied force, which is at 55 degrees above the horizontal. And there's a kinetic frictional force. Alright, so we can get into writing Newton's laws. In the y direction, sum of the forces equal to mass times acceleration. In the y direction, we have a normal force upward. We have a component of the applied force upward, and you can see there's a gravitational force downward. There is zero acceleration in the y direction. So in the y direction, we can determine that our normal force is equal to mg minus applied force sine theta. In the x direction, we can see we have a component of the applied force, and then in the opposite direction we have the kinetic frictional force, which we know is equal to mu k times normal force. That's equal to ma. Now we know that normal force is equal to this, so substituting, we then get Fa cosine theta minus mu k times normal force, which is mg minus Fa sine theta, is equal to ma. Well, and actually, as long as we're here, we'll divide by mass to get our expression for the acceleration of the sled. And then we can punch numbers in. Our mass is 22 kilograms. Applied force is 110 newtons at an angle of 55 degrees minus coefficient of friction is 0.3 times 22 times 9.8 minus applied force, still 110 sine theta. And then we plug and chug to find out what that is. 22 times 9.8 minus 110 sine 55 times negative 0.3 plus 110 cosine 55 divided by 22. We get an acceleration of 1.15. I'll stop at 7 meters per second squared. Alright, on to the next problem. Good old inclined plane. So, this time we have an inclined plane. The plane is indeed angled. So we are on our inclined plane. Our angle, 19 degrees. Okay, so my picture is way more than 19 degrees. That's okay. And then we want to know what forces are acting. Well, as always, we've got gravity, normal force, and then what else is going on? It's just sliding. There's no extra applied force. Nobody's pushing it or anything. So then we just have kinetic friction. All right, and with our inclined plane, remember, we rotate our coordinate system to align with the directions parallel to and perpendicular to the ramp. And once we do that, then we can start writing our equations. In the y direction, we have normal force going straight in the y direction. We have a component of gravity, which you should recall we worked out is actually mg cosine of the angle of incline of the ramp. And there is no acceleration perpendicular to the ramp. The block doesn't jump off the ramp, nor does it fall through the ramp. So we can see that our normal force is equal to mg cosine theta in this case. And then in the horizontal, or not the horizontal direction, sorry, the direction parallel to the ramp, we have a component of gravity that acts, and then we have kinetic friction, which is mu k times normal force, and in this case we know normal force is mg cosine theta. Interesting thing you notice here is that it doesn't matter what the mass of the object is, the acceleration is totally independent of the mass. Okay. And then the question is, how long does it take to travel this distance if its initial speed is that? So then we're going to take this acceleration and stick it into, well, what do we have? We have a distance, we have an initial velocity, we want to know how long, and we're calculating an acceleration. So we're going to stick it into a kinematic equation. Yeah, so that's what we got. Delta x equals v naught t plus 1/2 g sine theta minus mu k cosine theta t squared. So delta x, actually let's move that over because that's what we're going to do. Negative delta x equals 0. So then into our calculators we can type in 0 equals negative 2.3 plus 0.5t plus 1/2 9.8 sine 19 minus mu k, which is 0.21 cosine 19 t squared. Stick that in our graph, and we can find the amount of time it takes. It's good for you to remember that, kinematics is still out there. It will be something that will show up on the AP exam, and the AP exam is particularly fond of combining different areas in a question. The one that the negative time doesn't count. You can see that R0, our time is going to be close to a second. Left bound 0, right bound 2, guess 1. And so we can see this takes 1.084, call that 1.08 seconds. All right. Now carrying on. Pull at a constant speed. If I rope this angle at theta above the horizontal, rope this tension T, find an expression for the coefficient of friction between the box and the floor in terms of mt, theta, and g. Constant speed, that tells you acceleration is 0. And this is exactly the same as this guy up here. So our force diagram looks exactly the same as that. We've got gravity, we've got normal force, we've got tension, and we've got kinetic friction. And our equations are exactly the same as up here. So instead of working back through it, I'm going to jump straight over to this guy. Well, I'll jump straight over here. This comes tension cosine theta minus mu k times normal force, and normal force is mg minus tension sine theta, and that is equal to 0 because we're going at a constant technically I should say constant velocity. In theory, the box could be pulled in a circle and then it would have constant speed, but the acceleration wouldn't be 0. Yeah, so once we've got this, we just solve for mu k, move this over, divide out this chunk, and we get that mu k is equal to t cosine theta over mg minus t sine theta. And you can do funky stuff to factor that, but I would just leave it like that. Now, if the tension in the rope decreased, what effect would that have on the magnitude of the frictional force? Well, no, that's tricky. But to figure this out, we can go back to our y equation. In the y direction, we have normal force plus t sine theta minus mg. And that's going to be equal to 0. So if the tension, so then the frictional force is proportional to the normal force. So normal force is mg minus t sine theta. So If tension goes down, you're subtracting something smaller. That means the normal force is larger, which means the frictional force is increasing. So if tension goes down, normal force goes up, and friction is proportional to normal force, so frictional force goes up. To give a fully correct answer on a quiz or test or whatever, you should insert some words in here. Applying Newton's second law in the vertical direction yields this, which means that normal force is equal to this. So as tension goes down, normal force goes up, and frictional force is proportional to normal force. So as tension decreases, friction would increase.